Okay, yeah, this is a good question. Spoiler alert, sorry, that's the answer. So ignore that for the moment. So we're told that this relationship between distance and speed, braking distance and speed, is this, and that's the graph of that. And this is an exponential growth, exponential growth. But then we're told that if you log both axes, you get a straight line, and we see that in stats with regression that with exponential relationships and with power relationships, y equals x squared, you can get a straight line by either logging one of the axes or both of the axes. And that means you can use regression. You can work out the equation of the line of best fit and measure how well the points line up. But this is pure, and so this is sort of testing the same sort of thing. So what I'm going to do is I'm going to take that equation and log both sides of the equation. So the log of that and the log of that, and then I'm going to use the log rules to split this up. So that's the first log rule in reverse. Normally we say that becomes that. Now we're separating it, and then this, the n comes down. Now don't forget that we are plotting it on this graph here. So x is log of y of v and y is log of d. So if we look at what we've got here, this looks a little bit like a normal y equals mx plus c equation, because we've got y is log d, yep, check, and we've got log v there, which is our x, so that's our x, so that means this must be m, so that's the gradient of the line. And then this thing here is a constant, so that's our plus c, that's where the graph crosses the y-axis. Well, we know where the graph crosses the y-axis, we're told it. So I know that log k must be minus 1.77, so I can undo logging, and it's log to the base 10 in this question. We're given that steer from the axes there, log to the base 10, so we undo that by doing 10 to the power of, which gives me what I'm after. So that's the that's how I would explain this using that part. But I can then go on and complete the equation. So if I go back to the original equation here, that is the curve that I get from that equation. Now I now know what k is. I could use 0.017, or I could use the exact value, which is that. And it's unclear from the mark scheme whether they're happy with that, so I'm just going to stick to that. So that there is 10 to the minus 1.77, which rounds to that. And we've got a point here. We know that when v is 20, sorry, when v is 30, d is 20. So if I substitute those in, I get an equation with a missing value in the power. So I'm going to solve that using logs, but I'm firstly going to divide both sides by that. I'm then going to log both sides, and I could use whatever value, whatever base of logs I want, and then use the third log rule to bring, right, this is n log 30, and then divide both sides by log 30. That gives me that. Now I've sort of skipped those steps. I'm happy to go through that with you in person if you want. That tells me what n is. So I've worked out what k is. I've worked out what n is. So I can now rewrite that. There we go. That's k, and that's n. And it's that allows us to answer this question here. So you've got to say, right, 0.8 seconds travelling at 60 kilometres per hour. How far is he going to go? And then 60 kilometres per hour, what's the distance it's going to take for him to brake from 60? So you make v equal to 60, calculate the value of d, the distance, add on how far he will go in 0.8 seconds if he's travelling at 60 miles an hour. That's before he's applied the brake, so he's travelling at constant speed then. And that will tell you whether or not he stops before 100 metres. Now it's quite hard to explain this by video. Maybe it's better for me to do this when I see you in person on Monday or Tuesday, but yeah, hopefully that's helpful to a certain extent.